Okay, we are recording. Now class, we're in section 13.4. We're going to talk about a theorem called Green's theorem, named after the English scientist George Green. He lived from 1793 to 1841, and he actually worked. There's a biographical note in the book about him. He worked full time in his father's bakery from age of 9 and taught himself mathematics from library books. Okay, and then he self-taught himself, and they give information, but he entered Cambridge at age 40 as an undergraduate student. Uh, he probably, I'm not an expert on mathematical history, but probably accepted him because he had this mathematical skill, and but it says he died 4 years after graduation. That's unfortunate. But back in the 1800s, sometimes people didn't live so long, But anyway, this Green's theorem is named after him. And so, what is Green's theorem? All right. Well, let's go ahead here and look at the little highlighted thing. So, Green's theorem gives the relationship between a line integral around a simple closed curve C and a double integral over the plane region D bounded by C. So in stating Green's theorem, we use all right, so let's get to a picture. Let's get to a picture right here. So figure 1, okay, you have a contour, a path C that's closed. Now, Green's theorem is when you have a closed path, and the particle is moving counterclockwise in the figure 1, and we call that positive orientation. If the particle is moving around the closed curve counterclockwise, that's called positive orientation. And you notice that the closed curve C contains a region D. So figure 1 shows positive orientation. Figure 2, we have positive orientation in the left-hand side for that region D. And then on the right picture in figure 2 is negative orientation. So in the right picture in figure 2, there's a closed path, encloses a region D, and the particle's moving in a clockwise direction. So, okay, let's get to Green's theorem. All right, let me just highlight it here. Green's theorem says let curve C be a positively oriented, piecewise smooth, simple closed curve in a plane, and let D be the region bounded by that closed curve C. If P and Q have continuous partial derivatives on an open region that contains D, then the sum of the two line integrals on the left side, okay, with respect to x and y, the sum of those line integrals is equal to the double integral on the right-hand side. And they note that recall that the left side of this equation in Green's theorem is simply another way of writing that line integral, the integral of f dot of the vector field dot dr over curve C, where the vector field has components P and Q. So you are computing work. With Green's theorem, you are computing the work that the vector field does in moving the particle once around a closed path in its field. The path has to be closed for Green's theorem. And they talk about a proof of this. They go over a proof of it in in the book, and I'll let you look at that proof if you want. But it mentions in the biographical note that George Green, who came up with this theorem, well, he was the first person to try to formulate a mathematical theory of electricity and magnetism, and his work is the basis for electromagnetic theories that came later of Thomson, Stokes, Rayleigh, and Maxwell. So I can just I sort of verbally mentioned it because I didn't want to just mention it and not. Sometimes in the ebook it's can be a little difficult to find the biographical notes, but it's there somewhere. But at any rate, that's fine. So I want to just go to the whiteboard for a moment here, and I want to write the Green's theorem down. Section 13.4. All right, just making sure. All right. And of course, C is, well, this whole left-hand side here is equivalent to this line integral, which you know stands for work. Okay, and we note that C is closed for Green's theorem. Now, Green's theorem says, okay, this line integral is equal to the double integral over region D, where you have the difference of these partial derivatives, okay? The double integral of the difference of the partial derivatives. Now let me ask you this. Okay, let me ask you this. If partial derivative of q with respect to x equals the partial derivative of p with respect to y, then what can we say about our vector field? By the way, I'll mention the fact that the sum of these two line integrals being equal to the work, we proved that. We actually proved that last week. So, but let's focus here. I want to know, in the case that the partial derivative of q with respect to x equals the partial derivative of p with respect to y, what can we say about our vector field F? What would it be? What's this criterion used to show for a two-dimensional vector field? That's right, Noria. That's right, Lexi. The vector field F is conservative. Absolutely. And what would this difference here, what would it equal when those partial derivatives are equal? What does that equal? What is this integrand of the double integral equal when the partial derivative of q with respect to x equals the partial derivative of p with respect to y? What would the difference of those partial derivatives equal? What would it have to equal? That's right, Ashik. 0. So that means then that in that case, the double integral would equal 0, and the work would equal 0. So this means this actually makes perfect sense. We learned that when you have a conservative vector field, okay, the work along, if you have a starting point, you have some starting point, A, and you do one path, okay, around. If that's, and I want to make it smooth, okay, but if that's your curve C, and you move one, you start at point A, and you go once around, your path C is closed, and you return to point A. If you have a conservative vector field, the work that the force field does in helping move that particle along that path is equal to 0. So this is like the gravitational field. Think about the gravitational field. Gravitational field, if you're going up like this, the work is negative. The work is negative, right? Gravitational field acts against upward movement because gravity is pulling you down. But then when you go downward, okay, you go downward here, the work that the gravity does is positive on that part of the path. So the net work is equal to 0, gravitational field. That's an example of a conservative vector field. So I always like to talk about this because for some students, of course, here I am just giving you a formula, and we haven't formally proved it. It's in the book, the proof, but we haven't formally proved it. But intuitively, the formula should make sense because when you have a conservative vector field, the work along a closed path in that conservative vector field is equal to 0. Okay, so it's certainly, and it would have to be. So it would make absolute sense that, hey, you would have this as hold on here. You would have this difference here as your integrand. So, okay, let's go back to the book. Let's go back to the book, and let's look at an example here. So in example 1, I'll mention this too. So remember, Green's theorem is the work when you are moving along your closed path in a counterclockwise direction. Of course, if you are moving along your path in a clockwise direction, you can use Green's theorem. You just have to do what? You have to take the negative of your work value, right? That would be what you would do. So, okay, there is notation that sometimes comes up. The notation that you see here in the highlighted line integrals, well, remember the sum of those two line integrals is equal to the work value. If along a path that's counterclockwise, you see how they put a circle on the integral? You see that? So this notation is, let me just highlight. I always like to kind of have things very clear. That notation where they put a circle on the integral indicates the line integral is calculated using positive orientation of the closed curve C. Okay, so that is notation that you will see. And also, this is another kind of notation that you could see, where you have positively, that your boundary curve is positively oriented. Okay, so let's look at Green's theorem here in an example. And you can look at the proof. So in example 1, they want you to calculate a line integral. So here they want you to compute this line integral where C is a triangular curve consisting of line segments from 0, 0 to 1, 0, and then a line segment from 1, 0 to 0, 1, and then a line segment from 0, 1 to 0, 0. Okay, so pictorially, you are computing a line integral along this path. Notice the path C is closed and it contains 3 line segments. So if you were to use the concepts of section 13.2 to compute the line integral here, okay, they mention that although the given line integral could be evaluated as usual by the methods of section 13.2, okay, that would involve computing the line integrals across each path separately and finding the parameterization of each path separately and then adding up those line integrals. You could do it that way, but it would involve setting up 3 separate integrals along the 3 sides of the triangle. That's a lot of work. That's a lot of work. You've already had practice, right, of where you've had to set up 2 line integrals, right? How many recall that in the homework where you had your path consisted of 2 line segments, and you had to get the parameterization for each line segment and add up the line integrals for each line segment. How many recall that in the homework? And maybe elsewhere. How many recall that? Okay, Norina recalls that. Absolutely, absolutely. So, and Simon recalls that. Good, good. So, but remember in those instances, the paths were not closed, so you had to find the line integral that way. But if you have a closed path, you can use Green's theorem. And that's what they do here. That's what they do. So what they do here, if you notice in figure 4, the closed path encloses a region D, which is a triangular region. Well, you have done double integrals over triangular regions like that. Now you could integrate with respect to y first and then x, or x and then y. It doesn't matter. But you know, you've done double integrals over region D's like that before. And so using Green's theorem, okay, take a look at it. Take a look at it. The region D, that triangular region, is bounded below by the line y equals 0 and above by the line y equals 1 minus x, and then x goes from 0 to 1. So we end up getting, for the line integral, we get 1/6. So that's pretty nice, right? That's a lot easier than adding up 3 separate line integrals. Are there any questions on that problem? All right. Well, then let's do an example that I have for you. One moment. Let me bring this up here. Okay, let me give you a moment to copy this example down. Okay? Take a moment to copy this example down. And please let me know if you have any questions. Okay, so let's talk about this problem. So here we have a particle that starts at the point -2, 0, moves along the x-axis to 2, 0, and then along the semicircle, y equals square root of 4 minus x squared, to the starting point. Okay, so if we think about that semicircle, okay, just for a moment here. So the semicircle is y equals positive square root of 4 minus x squared. If we square both sides, we get y squared equals 4 minus x squared, or x squared plus y squared equals 4. So this gives us a circle centered at the origin with radius 2. So, I mean, this, of course, well, all I'm trying to do is when they say here, you know, here's the semicircle. Okay, so that's half of a circle. And I think, okay, what's the radius? What's the center? Well, if you square both sides, you show that this semicircle comes from a circle of radius 2 centered at the origin. So it makes perfect sense that that semicircle would go from the point 2, 0 to back to the point -2, 0, which is the starting point. We want to find the work done on the particle that moves along this semicircular path with, of course, the line segment below, if this is your force field. Now, what's the first thing you think we should do? Let's say you had a problem like this in your homework or on the final exam. What's the first thing you would probably need to do this problem? What would be very helpful to get you started on this problem? Any ideas? That's right, Lexi. Let's draw it. We want to know what our region D is. So, okay, here's the region D. There it is. So we started at -2, 0. Hold on. Let's get that loose. Okay, we started at -2, 0 here. Okay, and then we go from -2, 0 to 2, 0. And then we go along that semicircle with radius 2. And that gets us back at our starting point. So our curve C is closed and positive orientation. Curve C has it's positively oriented because it goes counterclockwise. The particle moves counterclockwise. So since C is a simply closed, positively oriented curve, the work done by the force field in moving the particle once around the path is by Green's theorem given. We can compute this double integral to get it. So you see what you learn with double integrals now is coming back. Remember, you learned that in chapter 12, and now you're seeing how it relates to chapter 13. Everything in all the material you learned from chapters 9 through 12 is going to come to play in chapter 13, or at least most of it. Let's put it that way. And a good portion of the exam, the final exam, will be on chapter 13. You have new material here that you have not been tested on, right? So certainly that's important for the final exam. Now you might notice for this double integral that I just mentioned, it's a double integral over some region D, and the dA, well, we have to decide on what dA is going to be. So of course dA, you could do dy dx, dx dy, and what's the third choice? dy dx, dx dy. What's another dA entity? One that might be helpful for this region. All right, good, Norina. R dr d theta, right? R dr d theta. So based on this region D, what do you think might be best to use? Rectangular coordinates or polar coordinates? What do you think would be best? Based on region D. What might be the best choice? I agree, Ava. We should probably think about using polar. Okay, we're not there yet, but there's nothing wrong with thinking ahead a little bit. Are there any questions before we move to the next page here? So this is probably the best choice. Okay, well, we just go ahead then and use the Green's theorem. So here we go. All right, we're trying to compute this work. And we recognize the sum of the line integrals, these two line integrals, is equal to the work. But we use this notation, right? So I'll add a few things here. See here, I can be a little more. P of x and y, q of x and y, q of x and y, p of x and y. And this, by the way, is due to Green's theorem. Note, path C is closed. Green's theorem only works for two-dimensional vector fields, and the path C has to be closed in the vector field. If the path is open, then if it's not a closed path, then you cannot use Green's theorem directly. Okay, so hopefully everything is good. And we end up getting, well, if we use polar coordinates, the limits are very easy. the radius goes from 0 to 2, and theta goes from 0 to pi. 0 degrees to 180 degrees, because you have half of the circle there. And so now it just becomes a section 12.4 problem. I like to use the iteration symbols because then, of course, I recognize this inner integral it's a value. And values can be moved out in front of that outer integral. That value can be moved out in front of the outer integral. Okay, and so if we then compute this, we will end up getting 12 pi. So there's no question that this force field helps the particle move along its path because the work is positive. And if we were to use MATLAB to draw a picture of this space curve C, this closed space curve C, superimposed with the vector field, we would see that the vector field is overall helping that particle move along its path. And that might be useful on the final exam if you know, you have an answer that's not quite working out, you know. How many have gotten an answer, a positive answer, when maybe it was a negative answer, like you get a 4 for an answer. I mean, the 4 is the correct answer, but you got -4. How many maybe has that kind of thing happened on a test? All right, Yeva knows what I'm talking about. Well, if you got, and Norina knows, sure. So like if your work, you did this problem, you got a work of -12 pi, and you know, you put it in WebAssign there and it's not taking the answer, you're pretty sure, you know, you at least theoretically you think you're doing it right. You could probably pretty quickly get a picture drawn of the vector field and the space curve in the vector field and see if the work looked negative or positive. And then if the work looked positive, that would clue you in maybe where the problem is. So we talked about like Green's theorem. They talk about where the region D is a simple region. Okay, a simple region, and essentially, you know, a simple region. If you have any 2 points in the simple region, you can connect those points, and the line segment would be inside the region. Okay, but occasionally in math, you have regions that are unions of simple regions. Okay, so like for instance, if I go to the ebook here, if I go to the ebook, go down a little bit here. There's the the biographical note, by the way, on Green. Let me see here. So, okay, so I want to be careful how I phrase it. You can have extended versions of Green's theorem. Okay, like for instance, if you had in figure 6, you can have the union of two simple regions. Okay, region D1 and D2. And if you were to define two curves going around those simple regions, effectively you would see that C3 and negative C3, well, they would cancel each other out. So effectively, Green's theorem can be used for regions that are unions of simple regions. Okay, and like you see there in figure 7, it's the union of any union of non-overlapping simple regions. So, like for instance, and I'm talking about this because this I want you to be prepared in a future course. Okay, so like because remember, Green's theorem is to find the work that a force field does in moving a particle once around its path for a two-dimensional force field. Okay, so you have magnetic fields and so forth. So this is physics and engineering application material. So in example 4, they want you to find the work where C is the boundary of the semi-angular region D in the upper half plane between two circles, one with radius 1 and one with radius 2. Okay, well, that region there in figure 8, okay, you can use Green's theorem on that region, on that figure 8 region, because it can be thought of as the hold on here. It can be thought of as the union of simple regions, the union of simple regions. Okay, so, and I don't want to get too heavy into this, but I want to say this the right way. You can apply Green's theorem to compute the work for a region like figure 8, because Green's theorem can be used for when you have the finite union of non-overlapping simple regions, like they're showing in figure 7. And essentially, let me just hold on one moment here. One moment. You see, along each of the simple regions you see in figure 7, there are 4 of them. Or no, they have it divided up into, 4. Along the blue lines, if you add up Green's theorem for each of the simple regions, the work along the blue portions of the curves cancel each other out because they're going in opposite directions. Okay, so effectively it cancels out, and so it works out, so to speak. So in this problem here, for example 4, figure 8, here's Green's theorem for that particular problem. So it's really pretty cool. And they even talk about in the book how Green's theorem can be extended to apply to regions with holes in them, holes inside of them. Okay. like a region like you see in figure 9 and figure 10. And again, they're trying to give you an intuitive feel for why Green's theorem would work. So I think for the homework that you have, you're not going to have any regions that have holes in them. But I just wanted to mention it in passing so that in the future, when you take your course in, electromagnetism or so forth, you've seen Green's theorem and you have an idea of how it can be used. Okay, are there any questions on this before we stop the recording? Who's feeling reasonably good with Green's theorem, section 13.4? Okay, Logan is, wonderful. Matthew and Narina's kind of, okay. Well, I'm going to give you some time to work on section 13.4. So let me go ahead and close the recording here. Very good.